So, hello everyone, I'm Kolditz, and due to the short amount of time, I will just get down to business. Okay, so the way we optimize our database systems today is, or how we design them is, we try to push or to keep as much data as possible in main memory, and we try to keep all our cores busy. We do a lot of things to optimize our systems, to reduce query latency, and to improve increase query throughput. But what we kind of all forget is that we all make a fundamental implicit assumption here. And it's that the underlying hardware is reliable. And there's a lot of evidence out there which suggests that this will no longer be true in the near future. So people said that, okay, we have ECC DRAM, error correcting code DRAM, and that will solve all our problems. But let's have a look how it works. So some of you may know the row hammer problem. This is just one example of an issue which is a threat to the reliability of our hardware. And it works. I just want to shortly show you how it works. So on the left side, you see a DRAM array. And when I want to read something from main memory, I have to put voltage to this accessor row here and to some of the accessor columns. And if I do this in a very fast succession, it may happen actually that some of these bits in the surrounding rows actually change their state, which is known as a bit flip. So in their paper, they showed that they found up to 4 bit flips in a single ECC word. And ECC DRAM actually works so that it can correct a single bit flip. It can detect a double bit flip, but then we have seen on Monday in the demo keynote already that then the memory will send a SIG bus signal, and typically we don't catch this signal, and it will just kill our process. And what is with these guys here, with 3 and 4 bit flips? And it turns out that there's a very, very high probability that the hardware does not detect such an error, and that there is silent data corruption. And this in turn means that we will work on corrupt data during our query processing, right? So another thing is, Intel showed in 2005 that the relative error rate will increase exponentially with each new step when reducing the transistor feature size. So with each new technology node, the relative failure rate increases exponentially. So we have a lot of discussion on this in our paper. And the essence is here that hardware solutions just do not scale. So we cannot make the hardware detect all those errors. And so we have the benefit that we have a lot of knowledge in our database, right? So we know the data, we know the data distributions, and we know all the algorithms which work on our data. So what are the consequences for database systems with respect to increasing error rates? So first of all, it was shown that memory cells are much more susceptible to bit flips than logic gates. So we have to do something to protect our most precious good, right? And that's the data that we manage for our clients. And on the other hand, there's a very important problem that's hardware aging. And that means that the error rates will change over time. So during the lifetime of our server system, the amount of bit flips will just increase, and also the rate, how often they happen. And for query processing, this will mean that in our queries, we'll have false positives, false negatives, wrong joint partners, and wrong aggregates. So we have to do something here. And I just want to quickly outline how we solve this. So we use an arithmetic error coding that works the following. So for each and every integer value, d, we multiply a constant a onto it. And that's our code word. It's nothing more. Pretty simple. So let's take an example here. So we have datum 5 and, oops, oh no, sorry. So we have a constant a equals 7, and the code word then is just 35. And we call this encoding step hardening to distinguish from other domains like compression or security. And the reverse operation we call softening, and that's simply dividing our code word again by the constant. So 35 divided by 7 is 5 again, which is our original data. And error detection works by computing or testing the remainder of the division by a for being 0. And if this is not the case, if this is not 0, then we have detected a bit flip. So this is the advantage of this encoding is that it's super simple, right? It's just a few arithmetic operations. And what's also very important for the data management domain is that we can do arithmetic operations and comparisons directly on the code words. So when we use it in query processing, there's no decoding, operation, re-encoding involved, right? But as you may see already, those softening and error detection operations are painfully slow. And especially in the context of in-memory databases where we want to vectorize stuff, this is also not possible here in this case. So in our paper, we mainly address 3 challenges. And the first one is that we replay or we make faster softening and error detection. And it works the following. There are, for certain numbers, there are so-called multiplicative inverses. So we can replace the division with the multiplication of another number. And then we again get our original datum. And we can use this, fortunately, for faster error detection because now we have our decoded data and we can compare it against the largest and smallest encodable data value of our original data domain. So let's take, for instance, 8 bits. So if we have 8 bits, then the smallest value would be for signed integer minus 128, and the largest one would be 127, right? And we can just compare our decoded value against these bounds, and if the decoded value is outside, then we have a bit flip here, a detectable. And of course, now the only 2 operations we have is multiplication and a comparison here. So and these can, of course, be vectorized. So the second challenge is which A do we actually choose? And it turns out 2 things. First of all, the A determines how many bit flips we can detect. In principle, the larger the A, the more bit flips we can detect. But there's much more to it. You can read it in the paper. And it's also dependent on the data width. So especially regarding compression and stuff. So depending on how many bits we use for our data, we need always a different A. And you can see also in the paper we have a table there, and we can detect 4 and more bit flips per code word. And the third challenge we tackle is how to integrate all this into a database then. So you can put all these things into all of the physical operators here. And so our evaluation, we did it the following. We implemented a calm store prototype where we actually harden all integer business data. And we do error detection in each physical operator. That means whatever integer value we grab from memory or even from cache, we test that for bit flips. All the source code is open source here. You can download it and test it. So we took the SSB benchmark here and all 13 queries, different scale factors, 1 to 10. So and the average runtime overhead, so the runtime overhead for doing error detection on each and every value for the Scala case is between 10 to 26%, and for the vectorized version it's between 7 to 28%. Now the last question I want to pinpoint here is how good is it actually? So all the generic software approaches which try to deal with this stuff, do some sort of double modular redundancy. And this means that you store all your data twice, you do all your computations twice, then do a voting afterwards, whether it's both are the same. And this obviously, if you run such things sequentially, you obviously have 100% or slightly more than 2 times the runtime than before. And if we take the average over all our scale factors and queries, we are ahead, has around 20% overhead, and I think that this is pretty good. Okay, let's sum up what I've told you. So hardware is becoming less and less reliable on the one hand. We will have to deal with a lot of errors in the future. And on the other hand, the hardware techniques to deal with that just do not scale to the future error rates. So, and we have a lot of knowledge about our data and our algorithms and the data distribution and stuff. So we can do a lot here to do much better than all those generic approaches. And I'd be happy to tell you more in the poster session, which is right afterwards. Thank you.
Time for one quick question.
Yeah, thank you for the interesting talk. A quick question is on, you mentioned you are supporting integer data types, so many business data is actually strings. So do you have an idea how to carry it over to strings, maybe by adding some extra space or whatever?
So A encoding is not a silver bullet. So there are a lot of other interesting techniques, and you could use different error codes. But so for instance, checksums or stuff for large, arbitrary large values. But what you can also do is, you can see each individual character as an integer, right? And then you can encode each character. And I think that this has also another benefit, because even if there's something corrupt inside the string, you can still do prefix and suffix matching, for instance. So that's just one idea. So yeah, that would be, so we didn't try this in the paper, but it's definitely worth a try, so to do it later.
Thank you.
Let's thank Till again.